These LSTMs are really impressive. Can't wait to show them to you. Let's do it right away. We are going to start off with a quote-unquote vanilla LSTM. We'll get into some more clever abstractions on LSTMs later on. Let's just start with the vanilla one. I have a vanilla LSTM waiting for you here in this notebook. We are going to recreate it here by copying the RNN demo and making a few changes. So let's rename this to the vanilla LSTM demo, and we'll give it a new title. We'll call it a vanilla LSTM classifier. So we're going to classify IMDb reviews by their sentiment with a vanilla LSTM. Cool. Let's clear our output so that we have a fresh slate to work with. Our dependencies are going to stay largely the same. We're going to swap out the simple RNN layer for an LSTM layer. We can tidy things up by moving this guy up a row, and we can move the embedding in there too, just to tidy things up. Great, so now the only layer in a separate one is the one that we're calling out here, the new one that we're adding in. Everything else in terms of dependencies is going to stay the same. We should give the output directory a new name. We can call it vanilla LSTM. And we're going to make a number of changes. So the LSTM is a lot more efficient than the RNN. So we can move our epochs back down from 16 to 4. Our batch size, we can leave at 128. Number of dimensions in our vector space embedding. In fact, all of the parameters with respect to our vector space embedding, these 5 are staying the same. We are just going to change the name around here from the number of RNN cells to LSTM. And same thing with our dropout variable name. We're just going to change it from drop RNN to drop LSTM. Again, I'm not going to be using a dense layer after the LSTM. If you feel like trying that at home, you're most welcome to. Just like we had with the RNN, we're going to have embedding layer leading into LSTM right into the output layer. I couldn't get better results by putting the dense in between. You might. All right, let's, there we go. Set the hyperparameters, loading our data the same way, preprocessing our data the same way. In the architecture cell, we will be making some changes. So really just one. So everything is staying the same, our embedding is staying the same, dropout on the embedding in the same way. We're simply swapping out this simple RNN layer with an LSTM layer. And we need to change the names of our variables here. And LSTM and drop LSTM. Otherwise, everything's the same. So let's look at that architecture. Cool, looks right. A million parameters to train. Our model configuration is the same, checkpoints are the same, and training is the same too. The model is going to take longer than it did with the RNN to load into our GPU's memory. So we can have a look at that here. You can see how much memory is being used on the GPU here. You can see that slightly more of it is being used over time. Oh, now that it's not, I bet it's done, and back on the other screen we're running. Oh no, we're still filling up memory. And now we're done. Now the GPU is processing. You can see we switched from 0% GPU computation to 34%. Our memory has filled up to quite a bit of the memory that we have available. And the fan is, the temperature is heating up in there too. So we've gone from 38 degrees Celsius to 41 degrees Celsius in a few seconds. 43 Celsius now. You can see the wattage is moving around as well. It's about as much wattage, 275 watts potentially, as a lot of whole computers. And that probably means the GPU fan will be coming on soon. So here we are, our epochs are training. We won't go through the process of watching all this train. It takes, on my machine, about 35 seconds per epoch. let's skip ahead to the results by heading into our directory here where I've output all the completed results, and we can have a look at our vanilla LSTM notebook. Over here we can see that the epoch with the highest validation accuracy is epoch 2, and it had 85.2% accuracy. So we load that model in and run our predict probability method on the validation data set, use those y-hats to examine the plot. We've gone from, remember in our RNN demo, we had a lot less conviction in the output probabilities. Now with our vanilla LSTM, we're back to quite a lot of conviction, a lot of probabilities near 0 or near 1, and that's reflected in a much higher AUC score again. So we've gone back from 84% of the area under the curve to 93%, which is great, not quite as good as we were getting with the convolutional network. So we were having slightly higher performance. In our demo, we got up to 96% of the area under the curve. That is the benchmark that we're chasing with 89% validation accuracy. So that's it for LSTMs. I also want to show you gated recurrent units, GRUs, quickly. So we now have both of those options up on our arsenal. In practice, I never really use GRUs. I'll tell you why in a second. Let's convert this notebook over. So let's copy this notebook, the vanilla LSTM notebook, and we'll create a GRU demo notebook. I'm going to go in and turn and shut down the other notebooks that are running, particularly the vanilla LSTM demo now, because we were just running it and training with it. It's possible that GPU resources were being used, memory resources were still being held by that notebook. So now you can see we rerun the NVIDIA SMI and we went from using up nearly all of the memory available on the GPU to none of it, which is great. So now it's available for our GRU notebook. And you can see the GPU card is still pretty hot in there, but it's not working now, it's cooling off. So let's head to our GRU demo notebook. This is now a GRU classifier. So we're going to classify IMDb reviews by their sentiment with a GRU. To do that, we're just changing one dependency. Let's restart and clear our output so we're working with a blank slate. So everything is straightforward. So change LSTM to GRU. That's it in terms of dependencies. We should change our output directory so that our outputs are going into a new directory, GRU. And otherwise, that cell stays the same. Loading data is the same. Preprocessing data is the same. Oh, let's change these variable names to GRU and GRU. Doesn't really matter. That's just for clarity. That wouldn't affect the results at all. But it just makes it nicer here when we change our architecture names. So we're changing the cell name from GRU, from LSTM to GRU, and same thing for both of these variables. Great. And this should be ready. Let's have a look at the model summary. So now we have our GRU layer in there instead of the LSTM. You can see that there are about 100,000 fewer parameters. So we had more parameters in the LSTM model, almost 1 million. In the GRU one, we have 900,000, and that's a reflection of the GRU having one fewer gate. So compiling the model is the same, setting up the model checkpoint is the same, and training the model is also the same as with the LSTM. The reason why I never really use GRUs in practice is that they are so similar to LSTMs. LSTMs just have that one extra gate. So LSTMs can do everything that a GRU can do. If they don't need to use that extra gate, then they'll learn not to. I think we'll see in these results. Okay, there we go. So that didn't take very long to train. Our LSTM took a little bit longer per epoch, so about 34 seconds per epoch for the LSTM. The GRU was a little bit less at 28 seconds, and that reflects probably the 10% fewer parameters, that gate not being there. And how do the results compare? Well, our vanilla LSTM had the best epoch was 85.1% in the runs that I had, whereas the GRU demo, it's just slightly lower, 84.5%. The best epoch in terms of performance, these three are all pretty similar in terms of accuracy, but we can see the validation loss is slightly lower in the first epoch. So let's go with that one. Let's have a look at the weights from there. We can calculate our y hat, throw that into our area under the curve calculation, and we will be able to see our results. There we are. So again, quite a bit of conviction, certainly, especially on the low end. So the GRU has a lot of confidence on the negative sentiment. However, check out relative to the LSTM on the positive end here. So our LSTM had a ton of conviction on a lot of these positive cases, and the GRU did not. So that's pretty interesting. And the results bear out in our overall score. So the GRU has an area under the curve of 92.5%, and the LSTM has 93%. So qualitatively, though, looking at that shape, that conviction seems promising. That's it for the vanilla LSTM and GRU demo. As I said, in practice, I don't really ever see a need for using the GRUs, but you see them a lot in the literature. I wanted you guys to understand what they are, understand how easy it is to swap out your LSTM for a GRU. And you can try it in your models and see if you get better results, but I've never seen better results from a GRU relative to an LSTM. So now you understand how the various families of recurrent neural networks, the simple RNNs, the vanilla LSTMs, the GRUs work. Up next, we're going to get a little fancy with our architectures, start blending things together from over all of these live lessons, and we'll see how our results turn out.